So to begin with, I would like to thank Professor Yong-Jung Kim for this very nice introduction and especially for his invitation to Korea. It is a pleasure to be here in KAIST and to have already started a collaboration with him. So maybe I will permit to add something to my CV. I have 2 PhDs, and the first one was in Leiden with Professor Bert Pelletier. So just so that...
I just found from the math side.
Okay. So today I will talk about the large-term behavior of solutions of a non-local ordinary differential equation. And it is joint work with Hiroshi Matano from the University of Tokyo, Tannan Nguyen, who is a PhD student at Orsay, well, was a PhD student at Orsay, and joint between Hiroshi Matano and me, and Hendrik Weber from the University of Warwick. So, so I will, before describing what we really do today, I will try to describe our purpose. Our purpose is to study a non-local Allen-Cahn equation, which you have here, and I also write on the blackboard. So typically we study it with homogeneous Neumann boundary conditions and some initial condition which I will describe in a little while. And here, so we suppose that we will work on a domain omega, which is bounded and has a smooth boundary. And we will keep using this notation for average of a function. So, we will call this problem P epsilon. So, problem P epsilon was proposed more than 20 years ago by 2 Israeli, one Israeli and one American researcher, Rubinstein and Sternberg, as a model for phase separation in a binary mixture. So, typically we will assume that F is minus the derivative of a double well potential with equal wells. So F equals minus W, and W would have this shape. And for this seminar, it is very handy to think as F of U equals U, 1 minus U squared, as a typical example. So, what is the difficulty about such a problem? It looks rather simple. You just have one single PDE, but however, it is non-local. You see, this term here creates a lot of problem. So, imagine I would just have to study this problem. In fact, this is a local Allen-Cahn equation. It has been very, very much studied in literature. And you have beautiful and easy properties such that if initial data are ordered for the standard Allen-Cahn equation without this term, then at each term the solution orbits will be ordered. So when you have such a ordering property, a comparison principle you can do for studying the standard Allen-Cahn equation where we forget this term, you can do a lot with what's lower and upper solutions. Here we are into full trouble because of this non-local term here, we lose any comparison, or nearly any comparison. So, now what is known about this sort of problem? First of all, so here you have a small parameter epsilon. So the coefficient of the reaction term tends to infinity as epsilon tends to 0. So you see, f of u intuitively has to tend to its average, that is to a constant in space. So now suppose that gamma naught is a smooth hypersurface without boundary. Then what is known is that there exists a time t star positive and a smooth family of initial data, u0 epsilon, such that for each time between 0 and t star, u epsilon at time t converges to -1 in a subdomain omega t minus and to +1 in a subdomain omega t plus. And so we have that omega is a union of omega t minus and omega t plus at each time. So imagine two subdomains, omega t minus and omega t plus, which compose omega. This is an example. So u equals about 1 in omega t plus, and u epsilon equals about -1, is close to -1 in omega t minus. Then a question is this, there is a boundary, a moving boundary, gamma t, between omega t minus and omega t plus. And so a question is, what is the law for displacement of gamma t? So if you would have the standard Allen-Cahn equation, the answer would be that gamma t displaces itself by motion by mean curvature. The normal velocity of displacement of the interface is equal to its mean curvature. And it has been, as I told you before, very much studied. Maybe a first paper ever written about it was written by Bronsart and Kohn in a spherical symmetry. Then later this convergence was studied by Monotonicity, Schatzman, Xinfu Chen, and later by many other people. Now here you have a little change. You keep having this motion by mean curvature, but you have an extra term, which is the average of mean curvature on the moving interface, and this average is due to the presence of this average here. So this property was proved in two places. First, in collaboration with Xinfu Chen and Elisabeth Logach. And then we did not know about that work, but there are similar proofs given even before our paper by Koji Okada in Japan. So now there is an open problem, which is a generation of interface. When I talked about propagation of interface, the sort of result both Okada and us have is that the existence of some family u0 epsilon such that you have convergence to a moving boundary problem. So now let's take the question in a bit a different way. Given u0 rather arbitrary, would there be such a can we create such a motion of interface property? So of course there is a lot of things known again about the Allen-Cahn equation standard, and so then we know about what is called the generation of interface property. That is, on some very small term, the solution of the PDE of this PDE here behaves as the solution of the corresponding ODE, du dt equals 1 over epsilon squared f of u. And here we are going to have to study the corresponding ODE. So with us, we drop the term, the diffusion term, which we had here, but we keep the non-local term. And this is our motivation for starting our study of a non-local ordinary differential equation. So now we still have the small parameter 1 over epsilon squared here, and we work a priori on a small time interval 0 t epsilon, the time needed so that the solution creates an interface situation such that u epsilon at time epsilon is nearly everywhere close to -1 or close to 1. So the first thing we do is we change of time scale. We set tau equal t over epsilon squared. And so then all coefficients in the ordinary differential equation become of order 1. So we just have u tau equals f of u minus average of f of u with the same initial condition. And here we have the same space domain, but now we have to consider this ordinary differential equation on the time interval 0 t epsilon over epsilon squared. Of course, we have not yet proved, and we will not even do it today yet to reach it today. We have not yet proved anything about the order of t epsilon. But imagine that t epsilon over epsilon squared tends to infinity as epsilon tends to 0. And this will indeed be the case. Then the solution, what we expect is that the solution u epsilon of prime p epsilon will be very close to a function some function v infinity, where v infinity is a stationary solution of this problem ODE which you have here. And this is our motivation for studying this problem. So now what we will prove is that v infinity in general only takes two values, a minus and a plus, which are such that f of a minus equals f of a plus equals the same constant, say k, and f prime both at a minus and a plus is negative. The constant k here will depend on the initial data. So what will happen is that after time t epsilon, u epsilon will become close to either a minus or a plus with steep interfaces between the regions where u epsilon is close to a minus and u epsilon is close to a plus. So now from this moment on, we are going to concentrate on the non-local integral differential equation, except that I would like to tell you about other results which we got, this time considering the non-local Allen-Cahn equation with all coefficients of order 1. So we have Vt equals Laplacian V plus f of V minus average of f of V. Again, Neumann boundary conditions and some prescribed initial condition. And here we have worked with slightly different assumptions. We suppose that f has a form of a polynomial of degree n, with n at least equal to 3, or being another odd number, and an being strictly negative. So there, okay, you can check some very useful properties. You have first conservation of mass, or conservation of the integral, that is integral of v of x and t dx on omega is equal to integral of v naught of x dx. So how do you see such a property? Here we will have a smooth enough solution because we have a parabolic problem. So we integrate on omega. So we have ddt of integral of omega equals integral of Laplacian v, which vanishes because of the Neumann boundary condition, plus integral of f of v, minus integral of average of f of v, so this term will vanish. And we will have ddt of integral of v of x and t dx equals 0, and that's this property. Now, there is another useful property. It is we have a Lyapunov functional, that is a functional which decreases along solution orbits. So which is the same than for the standard Allen-Cahn equation, that is, we have E of v equals a half of integral of gradient squared minus capital F of v. So we have quite some properties at our disposal, besides not having any comparison principle. So with two young people, Samira Boussaïd and Tan Nam, we have applied a Loyasevich type inequality to show that as t tends to infinity, V of t stabilizes, converges to a stationary solution. So, in other words, the omega limit set of U naught is a singleton. Now, let us come back to the purpose of this lecture, namely this non-local ODE. So, for the rest of the lecture, we will cancel the term Laplacian U, cancel. So we just have ut equals f of u minus average of f of u. Because we have an ODE, we don't need any boundary condition anymore. And we still, of course, need some initial values. So this is the problem which we are going to study from now on. And I guess we call it a problem ODE. So now our assumptions for the function f are rather similar than what we made at the beginning. That is, f is smooth enough, say C1, and it has exactly 3 zeros. So f will be of such a form, and it has 3 zeros, A0, say, A minus, and A plus. Here you see that f prime will be strictly negative at A minus and A plus, and this will be stable zeros, whereas f prime of A naught will be positive, and this will be unstable zeros for such a ODE. So, and our aim is to study the omega limit set of U naught, that is a set of functions, say phi, for instance in L1, such that along a subsequence U of Tn converges to phi in L1 as Tn tends to infinity. So here I have you have essentially the same graph which we have here, and we will need some specific points. So here you have a small m which corresponds to the minimum of f, and capital M which corresponds to the maximum. Then what we do is we take S1 small enough and S2 large enough, so that f of s is always between f of s2 and f of s1 for s larger than s1 and smaller than s2. And we define two more constants. We define s lower star here. We define as f lower star by f lower star equals f of capital M, and and s upper star by this way, by f of s upper star equals f of small m. This is what is written here. So we have all the ingredients we need essentially for pursuing this seminar. So now we should discuss properties of this non-local ODE. First of all, one can see formally but also rigorously that this problem has again the mass conservation property which I had written here, so now with the function noted u. And we have again a Lyapunov function, E of u equals minus integral of capital F of u. And it is no surprise to get the idea of having such a Lyapunov function. All I take the notes which I had shown you before. when we had the diffusion term, the term Laplacian u, we had a term, a half of integral of gradient v squared here, but we have lost the diffusion term, so we don't put this term anymore, and this is what stays, and E of u equals minus integral of f of u will be, again, a Lyapunov functional. So, however, the solution of problem ODE will have some smoothness, but will not be as smooth as the solution of the diffusion problem which I showed you before. So, for instance, we don't know how to apply a Loyasevich type inequality, and our study of the large time behavior of the solution has to be done with other methods, and especially to study more precisely the profile of the solution u of t at each time. So here you have what I call hypothesis H1, which is very simple, so it will be the same for the rest of the talk. We have u naught belongs to L infinity of omega, and we'll have that u naught is between S1 and S2. So now I will show you our main results. So always assuming H1. So problem ODE possesses a unique solution U, which is C1 with values in L infinity of omega. Moreover, U is bounded from below by S1 and bounded from above by S2. So you see, that means that the segment S1, S2 is an invariant set. Having hypothesis H1, we can show that U at each time, U of x and t, I write just U of t on the blackboard, is between S1 and S2. And in fact, so many properties were proven formally in the paper of Rubinstein and Sternberg. At that time, they didn't prove existence, but they studied formally many properties, and in particular, they had already shown this property of the invariant set. So this is great because we know that the solution is bounded in L infinity. Now, we show, and I will give the ideas which we use, that omega of u naught is a non-empty compact connected set in L1. And so this is work. This is not at all trivial. When we have ut, if we add a Laplacian u term here, if we have a diffusion equation, it is very natural to perform a couple of a priori estimates to discover, for instance, because of the Lyapunov functionals, that the gradient of u is bounded in L2. And so this will give compactness in L1 or L2. But here we have no diffusion term, a priori nothing which helps to show that the solution regularizes in time. So you will see in a minute how we do. So then, so we will prove the compactness of the omega limit set. And now another property, suppose that phi is in the omega limit set of u naught. So then, because of the invariant set property, phi will necessarily be bounded from below by S1 and from above by S2. And we prove that it is a stationary solution of problem P. So a stationary solution, I obtain formally the equation for the stationary solution by replacing du dt by 0 here. So this is what's happening here. We have f of phi of x equals average of f of phi almost everywhere. So this characterizes stationary solutions of problem P. So now the first question is, how do we prove the relative compactness of the solution orbits with only supposing this hypothesis H1, that is that u naught is bounded in L infinity. So then what we do is we transform our arbitrary dimensional problem into a one-dimensional problem by applying a unidimensional monotone rearrangement. So we transform a function W into a non-increasing function W sharp in such a way that the measure of points of the set of points where W is larger than S coincides with the measure of the points where W sharp is larger than S. More precisely, we define W sharp. So on the one-dimensional corresponding domain, which we call omega sharp, that is 0 measure of omega, by omega sharp of 0 equals the supremum W sharp of 0 equals the supremum of W, and W sharp of S is defined as it is given here as the infimum of tau, such that the set of points where W is larger than tau is strictly less than S. So now, I will show you some properties, recall properties of monotone rearrangements. So those properties are well known, they can be found in a number of books, and I will quote one of them which we use. It's a book by KAIST, written a couple of years ago. So, for instance, so you have that if G of W is in L1, or if G is non-negative, then the integral stays preserved by the monotone rearrangement. That is to say that integral of G of W on omega is equal to the integral of 0 to measure of omega of G of W sharp. Then, if G is non-decreasing, we will have that the monotone rearrangement of G of W equals G of the monotone rearrangement of W. And then you have a third very useful property, but which will not be quite enough for us. We'll have to work a bit harder. So give P larger than 1 arbitrary, and suppose that W1 and W2 belong to LP of omega, then the norm in LP of 0 measure of omega of W1 sharp minus W2 sharp is less or equal than the LP norm of W1 minus W2. So these are the three properties which we will use in what follows. So, and now we will use these properties firstly to show that the rearranged function in one space dimension, U sharp, satisfies exactly the same problem than U, namely the same ordinary, non-local ordinary differential equation. So I apologize, I realize the notations have changed in the meanwhile. So I have used two notations for the same thing. Here average of f of u, and here another notation for the same thing. So we have u sharp t equals f of u sharp minus average of f of u sharp with the initial function that u sharp of x and 0 is a rearranged function of u naught of x. So now we are in one space dimension. When we have such a problem, note that we can do the same proof as before, because since u naught is between S1 and S2, u naught sharp will be between S1 and S2, and u sharp of t will also be between S1 and S2. And now it is also non-increasing, a non-increasing function in one space dimension. It implies that u sharp of t is bounded in BV of omega sharp, 0 measure of omega, by a constant c which only depends on S1 and S2. And so, because u sharp of t is bounded in BV, it is relatively compact in L1. Okay, so now what we have to do is justify that u sharp indeed satisfies this equation, and then we have to see how we can use this relative compactness of orbits of u sharp to deduce a similar property for u of t in arbitrary space dimension. So first of all, so consider again our non-local ODE. We set lambda of t equals average of f of u of t, and consider just this problem. This is a standard ODE, just non-autonomous because we have lambda of t here. So y prime equals f of y minus lambda of t, and y of 0 equals s. And one can show that the solution y of t and s of this problem is strictly increasing with respect to s. Also, you can observe that u of x and t is exactly equal to y of t and u naught of x. Except reasoning with u, we have a non-local ordinary differential equation. This is a bit hard for our intuition. And here we just have a standard ordinary differential equation. That means we see better, we visualize better that at each point of the space we have the same ordinary differential equation. Of course, it is just rephrasing what we have here. So now let's recall let's recall this property. We have G non-decreasing, and we had that the rearrange of G of W is G of the rearrange of W. So we will apply it here. Y is increasing with respect to S. So we have that U sharp of T, that is a sharp of Y of T and U naught, and that is equal to Y of T and U sharp naught. U naught sharp, sorry. So then this implies that we have that U sharp T equals F of U sharp minus lambda of T. And there, lambda of T, we just defined it as average of F of U of T. But we had another useful property here, that is that integral of G of W, if G was non-negative, was equal to the integral of G of W sharp on omega sharp. So we'll use it here, and we get that average of F of U is on omega is equal to the average of U sharp on omega sharp. And we have here, we see that we have exactly the same ordinary differential equation. So now we prove another very useful property. It is that the L1 norm on omega sharp of U sharp of T minus U sharp of tau for two arbitrary times T and tau is equal to the L1 norm on omega of U of T minus U of tau. And so from that we deduce that since the orbit U sharp is relatively compact in L1, also the orbit U of T is relatively compact in L1 of omega. So there we are. Now we have the result in arbitrary space dimension. So corollary, let Tn be a sequence of positive numbers such that Tn tends to infinity as n tends to infinity. Then the following statements are equivalent. U sharp of Tn tends to psi in L1 of omega sharp as Tn tends to infinity. And U of Tn tends to phi in L1 of omega with psi, the psi here is equal to phi sharp. So now, okay, we know that sequences U of Tn converge to some function as T tends to infinity, and we have to characterize further these functions of the omega limit set of U naught. And one of the properties we prove is that phi is composed, essentially takes three values, so A minus, A naught, A plus, on three sets, capital A minus, capital A naught, capital A plus, so phi equals A minus, characteristic function of capital A minus, plus A naught, characteristic function of A naught plus A plus characteristic function of A plus with omega equals A minus union A naught union A plus. And those sets do depend on phi. And the small A minus, A naught, and A plus are such that f of A minus equals f of A naught equals f of A plus equals the average of f of phi. So you see here, say you have the average of f of phi, and you have the three values which are equal. So then we have to try to go further with characterizing the omega limit set. So assume that again that H1 holds, and here we make some more assumption on U naught, namely that the initial function is the average of the initial function is outside the interval S lower star, S upper star. So either we have average of U naught less than S lower star, or average of U naught larger than S upper star. So from a phase transition viewpoint, it would sort of be the least interesting cases, but anyway. Then we prove that omega of U naught is composed of a unique element phi, and phi is the average of U naught. So we have only one value. And moreover, we have the convergence to stationary solution is exponentially fast. There exist positive constants C1 and C2, such that U of t minus average of U naught in the L infinity norm is less than C1 e to the power minus C2t. Okay, so now we can also look what is the situation when again we have H1, but this time average of U naught is in between S lower star, which we have here, and S upper star. So suppose that phi is in omega of U naught, then we have that average of f of phi is in between, bounded from below by f of small m and bounded from above by f of capital M. So you see that's where small m and capital M start playing a role. And there exist subdomains omega minus of infinity, omega naught of infinity, omega plus of infinity, such that, as I have shown you before, phi takes the three values A minus, A naught, and A plus. Again, those values are the roots of the equation f of s equals average of f of phi. So now we would like to refine this property and to try to characterize cases where there are not three values taken but two values. So remember that 0 is an unstable value, say typically for this simpler ordinary differential equation, that is A0 is repulsive, A minus and A plus are attracting. So we expect that in many cases only the values A minus and A plus will be taken. So here assume again that the average of U naught is between S lower star and S upper star, and assume furthermore that the measure of the point where U naught equals S for any S in R is equal to 0 for every S. Then omega of U naught only contains one element phi, and this phi is given by A minus chi of characteristic function of omega minus of infinity plus A plus characteristic function of omega plus of infinity. So here we have a complete characterization of the asymptotic behavior of U of t. So now I show you some auxiliary lemmas which help us to prove this result. So even though we have lost every real maximum principle or comparison theorem, we still have many nice monotonicity property. And this is what I will show you here. So first of all, if average of U naught is less than the value S lower star, then at some point there exists a time t naught such that U of x and t will be less than S lower star everywhere for t larger than t naught. On the opposite, if U naught, average of U naught is larger than S upper star, then there will exist t naught positive such that U of x and t is larger than S upper star for all t larger than t naught. Now, so here we have considered cases where average of U naught is outside of the interval S lower star, S upper star. Now let's consider the case where average of U naught is in between S lower star and S upper star. Then we will have that average of phi will be between f of S upper star and f of S lower star for all phi in omega of U naught. And there will exist t naught such that U of x and t is in between S lower star and S upper star for all t larger than t naught. So we have seen that in quite a few interesting cases, the ranges of the solutions are after some time completely inside the interval S lower star, S upper star, or completely outside this interval. So now I show you again I get another form of a proposition which you have already seen. We assume that H1 holds and U naught is between S lower star and S upper star. If phi is in omega of U naught, then there exists alpha which only depends on U naught, such that phi equals A minus the set of points where the characteristic set of the points where U naught is less than alpha, plus A naught, the characteristic points where U naught is equal to alpha, and plus A plus, the characteristic set of function where U naught is larger than alpha, where, again as before, A minus, A plus, and A naught are the roots of this equation, f of s equals average of f of phi. So now how can we characterize or not the functions of the omega limit set? We try to use all the relations which we know. We know that the Lyapunov functional, which I have shown you, minus integral of capital F of U, is constant on the omega limit set. That gives us one relation. We know that since the integral is preserved, that the integral of phi is equal to the integral of U naught. And we know that f of A minus equals f of A naught equals f of A plus, equals, so a value eta phi. And here we have, say, 4 equalities, but 6 unknowns. We have as unknowns the values A minus, A naught, and A plus, and the sets capital A minus, capital A naught, capital A plus. And so we need much more conditions to characterize functions of the omega limit set. However, in cases where we can prove that the measure of A naught equals 0, which is logical because A naught is an unstable point, then we have, it's a bit better because we have four relations and 4 unknowns, the values A minus and A plus, and the sets capital A minus and capital A plus. And also note, we constantly finally, we give all the proofs in arbitrary space dimension, but we always have in our mind the one-dimensional picture, which corresponds in a one-to-one way with arbitrary dimension picture. So we have only, if we have two values, for the rearranged function, we will first have the larger value, and then the smaller value, a plus and a minus. That's how the steady state will look at. So it is quite easy to figure out with what we work. So, and here you have a counter example where things don't work as fine. So take U naught like this. So non-zero here, but 0 on a whole segment here. And again non-zero. And assume f of s equals s minus s cubed. Then one can show that omega of U naught possesses a unique element phi, which has this form, so which is -1 in the set where U naught is negative, 0 on this whole segment where U naught equals 0, and 1 in the set where U naught is positive. So consequently, the measure of the set where U naught equals 0 is non-zero here, and the measure of the set capital A naught is also non-zero. So three values are taken for the function phi from the omega limit set, from the stationary solution. So now I will show you a key lemma, which again has a form of a monotonicity lemma, and where small m and capital M have a key role. We call omega minus of t the set of points where U is less than small m, omega naught the set of points where U is between small m and capital M, and omega plus of t the set of points where U is larger than m. And so our key lemma is the following. Assume that U naught is between S lower star and S upper star. Then omega minus expands, omega plus expands, and omega naught shrinks. So which is natural. The sets. So we consider. I should simplify or redo that graph. I am going to redo the same graph, but just try to simplify it a bit. It contains now too many values. So sorry, I waste a bit your time, but here we have small m, and we have the unstable 0 here. We have capital M, and we have the stable 0 here and here. So it is very natural that the set of points where U is between small m and capital M, and which contains the unstable 0, shrinks, and the set of points containing the stable zeros, A minus and A plus, increase in time. So of course we will have only, we can justify that functions of the omega limit set take only two values, A minus and A naught, if we can prove that such a set shrinks to at most a single point when t tends to infinity. So, and now the argument to prove this property, which I have shown you before, is rather simple. If at some point x and some time t, U is less than small m, because we have that non-local ODE, then at each time larger than t, and in the same point x, U will be less than m. And similarly, if U at x and t is larger than capital M, U at that same point x and all later terms will be larger than capital M. And so this is why there is the two sets, omega minus and omega plus expand. So I thank you for your attention.